I'm going to wait like a minute, like until 1 o'clock, until everybody's in the Zoom.
Hi, my name is Amy Sullivan, and I'm the chair of the AAAR Endowment Committee. It's my pleasure to welcome you to our 11th in our monthly series of ASNT lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So the idea behind these lectures is to help to provide a forum to show off our amazing research to our community, also give us an opportunity to all come together outside of the conference, and also to tie our journal to other activities. So each month, a high impact paper is selected by the editors of ASNT to be presented by its authors. These lectures are being recorded, and you can watch them later on AAAR's new YouTube channel, which you can access from the AAAR webpage under the Events tab. In addition, each month, one of our student chapters is hosting the lecture. So I want to thank everyone who's made these lectures possible, and also all of you for joining us. And so now I'll turn it over to our student chapter from Clarkson University to get us started. Thanks.
Thanks, Amy. Hi, all. I'm Chaitani from the research group of Professor Daniela of Clarkson University. I'd like to welcome you all to the April ASNT lecture on behalf of Clarkson University student chapter. Today, our lecture is going to be a very beneficial one to those who are working on aerosol sampling, especially bioaerosols. So today's speaker for us is a specialist on infectious aerosol sampling and characterizing them, Professor Shana Ratnasar Shumate. We warmly welcome you. Professor Shana is an associate professor in the Department of Pathology and Microbiology at University of Nebraska Medical Center. She is a lecturer for the Biological Defense and Health Security at the same university. And she also is an affiliate of the Global Center for Health Security. She also serves as a fellow of the National Strategic Research Institute for the US Department of Defense and an adjunct faculty for the University of Nebraska Lincoln Morrison Center. Some details into Professor Shana's background. She received her bachelor's and master's in environmental engineering sciences at University of Florida, and she received her PhD in biochemical and environmental engineering at University of Maryland, Baltimore County. I wish I had more time to mention about her many contributions to the field of aerosol science and technology, but I would conclude this introduction thanking her for her involvement in our field and in ASNT Journal as an editor. Professor Shana, the floor is yours.
Thank you, Chaitani. Thank you for the opportunity, Dr. Sullivan, and also Dr. Reed for inviting me to present today during the lecture series, and the Clarkson student chapter for inviting me to present as well this week. I'd like to start by highlighting a recent win for the aerosol sciences community. A recent statement was released by Dr. Alondra Nelson from the White House Office of Science and Technology and Policy, which I think has been part of a very long fought scientific battle between the aerosol sciences community and the general sciences community about the role that aerosols play in the transmission of COVID-19. And I'd like to give credit and kudos to all of the leaders within the AAAR community for basically working very diligently to educate the media, the policymakers, the clinicians, and the general public about the science of aerosols, and to really help to make this significant change in our perception of how COVID is being transmitted. It's a small step in the right direction, especially as we start to see cases of COVID start to decline again in the global population and in the United States. It is in direct contrast with what our current public health policymakers at the WHO and CDC are currently still stating in terms of transmission of COVID-19, but we are seeing other policy and organizations within the US government, such as the EPA, take steps in the right direction to basically provide standards towards mitigation. This is no surprise to most of the members who are attending today, but aerosol science has played a significant role in public health traditionally. However, very small aspects of it have actually been incorporated into a lot of the countermeasures and preventative measures that are utilized by the clinical and public health community in terms of preventing the spread of infectious diseases. Aerosol science specifically has a lot to do with how the sources of the infection, the sources of materials from infected individual or infectious sources, such as in agricultural pathogens, and being able to measure those sources in terms of studies to look at prevention of infection, personal protective equipment, how we need to appropriately quarantine, social distancing practices. Specifically now, a lot of work is being done in ventilation, but also in therapeutics and therapeutic development. We also see aerosol sciences utilized a lot in survival studies to understand environmental management, so outdoor versus indoor conditions, and in a lot of animal models for infection in order to help develop therapeutics and other types of countermeasures to infectious diseases. So as far as how aerosol measurements are made, we look at aerosol sciences in the aerobiological pathway or in the public health community through three different sort of components. The first is sources. So needing to understand the particle composition and concentration of infectious materials or other types of aerosol, biological aerosols, and where they come from. Understanding the distribution and the influence of the local environment, not only on that distribution, but also on what's going on inside that particle as it's released into the environment and equilibrates within that environment. And also looking at things like how do disease progression, such as the infectivity or the concentration of material from an infected individual or infected host, how those change as a function of time. All of these contribute to sources, and all of these require some form of measurement in order to assess them. In the environment, again, we're looking at the stability of the infectious material as a function of time and the environmental conditions. How do things like temperature, relative humidity, sunlight impact the stability of the organisms as they move through the environment from the source to a host? And then a significant number of studies look at the transport and dispersion, not only outdoors, but indoors, looking at HVAC and air movement pockets, transport within indoor conditions from room to room, from person to person, from patient to clinician. And then there's the health effect pieces. What are the deposited amounts? How is the host responding to the deposited amount? What are sort of dose-dependent responses that we can measure in, for example, animal studies to determine the infectious dose or the lethal dose of a specific infectious disease? And then how do those manifest in the host? In all of these various components in the aerobiological pathway, some type of sampling device or instrument is utilized to quantify these measures. And ultimately, these are used to then determine the risk of the source leading to an infection and to inform mitigation strategies. And in essence, mitigation strategies and developing and evaluating and testing mitigation strategies are also using aerosol sampling equipment. So early during the COVID pandemic, there were a number of studies that came out during the sort of late spring, early summer of 2020, characterizing not only the sources of SARS-CoV-2, the virus that causes COVID-19 in aerosols, but also studies looking at its persistence in the environment, as well as early studies to try to determine the infectious dose. And for most of us who were performing work with SARS-CoV-2 at that time, resources became extremely limited in terms of the supply chain and our ability to acquire materials. And so most of these studies utilized what researchers had in hand at the time in order to measure these various parameters. And we start to see an emergence of a number of different types of biological aerosol or just aerosol sampling devices that are employed. For example, the University of Florida performed some studies early on with the BioSpat Vivus, which is a condensation-based bioaerosol sampling device, and was one of the first institutions to be able to sample infectious SARS-CoV-2 virus near infected individuals. The University of Nebraska Medical Center utilized Sartorius MD8 filters. in order to sample SARS-CoV-2 in a clinical setting, and was also able to demonstrate infectious material. And then we saw a number of studies where impactors as well as filters were utilized to detect and quantify concentrations of RNA, again, around infected individuals. But all of these utilized different samplers. And even at the studies that were performed at the NBAC at the time, which is where the study that I'm about to speak about was performed, we were beginning a number of studies and utilizing gelatin filters to determine the persistence of SARS-CoV-2 over time, but really wanted to be able to understand how our data would correlate back to the various other studies that were being performed that were determining source, as well as future studies that were going to determine infectious doses. And so that was sort of the reason for performing the study that I'm presenting on today. So really quickly, it is a pretty well-established phenomenon in the aerosol science community. And for those of us who have been performing bioaerosol research for the better parts of our careers, that this is a particular challenge to work with bioaerosols, specifically because there are so many devices that are out there and available for use, but that it is known that the device can influence the amount of infectious material that is recovered. We can see influences based on the physical capture efficiency or sampling efficiency of the devices. So that's based on the particle size distribution, as well as specific influences of the type of device that are specific to the organism that's being sampled. Dr. Manelis actually did a really great review as part of a special issue of bioaerosols and AS&T back in 2019, and talks a lot about the influences of different devices and all of the parameters that affect the concentration that's sampled and recovered. But these are two examples for specifically for viruses where we can see that just based on two different devices, the amount of material, or in this case, influenza virus measured with the Vivus aerosol sampler as well as the biosampler can be significantly different, where the Vivus samples nearly 100% of influenza virus and is able to maintain the infectivity versus the biosampler where you see significant losses and deviations from the actual concentration in the air. Similar data were developed by NBAC for Ebola virus, where we can see midget impingers versus the BC251, the all glass impinger biosampler and gelatin filter, where there are significant differences at low relative humidities. I should point out these white dots are low relative humidities versus dark relative humidities in the amount of virus that's measured. So it is because of these differences that we know occur and that they are specific to the devices that are being tested, as well as the organism being tested and this particle size distribution, that we wanted to evaluate and determine which laboratory scale aerosol sampling device was going to be most appropriate for studying SARS-CoV-2. So we looked at essentially 8 different samplers. Of course, these were ones that were readily available to us at the time, since this was early in the pandemic, as well as those that we had seen emerging throughout the literature and those preliminary publications on SARS-CoV-2 aerosols in many of the studies. We looked at the all glass impinger, the AGI-4, which is commonly used in most in vivo studies in animals across most of the institutions that perform those types of studies and is the current standard. We also looked at the biosampler, which was developed because of the losses that had been observed historically in all glass impingers of viral aerosols, and is a more gentle impingement technique and is intended to maintain the integrity of the bioaerosol being sampled. We also utilized glass midget impingers, which were utilized in, I believe, one study performed early on for SARS-CoV-2, looking at the stability of the virus in aerosols, as well as PFA midget impingers. Now, the PFA midget impingers were intended to identify whether they would serve as a good surrogate for glass midget impingers, specifically because SARS-CoV-2 aerosols need to be studied by safety level 3 containment, which can be challenging when you are working with glass materials if you break one. So we wanted to identify whether PFA would be a good replacement for any of these impingers. The Ciotis impactor was utilized in a few early studies in Wuhan to look at the size distribution of SARS-CoV-2 in a clinical setting. We looked at gelatin filters. We looked at 47 millimeter gelatin filters, assuming that the recovery on 47 millimeters would be very similar to the 80 millimeters that are typically used in the Sartorius MD8. We were able to use a BC251 sampler from NIOSH which was loaned to us by Dr. Bill Lindsley. And also midway through 2020, summer 2020, the gelatin filters very quickly became limited, and we had to find an alternative. That was basically a supply chain issue that no one saw was going to happen during COVID. And so we decided to look at Teflon filters, which are the filters that actually are utilized in the COTIS per the manufacturer's guidelines, to see how well they compare to gelatin filters in terms of their ability to sample and maintain SARS-CoV-2 in aerosols. So really quickly, in terms of how we performed our studies, we worked with SARS-CoV-2, one of the first isolates of the virus that was taken from one of the Washington cases. The virus was propagated in Aerosols in a viral culture media with 10% FBS. After the virus was produced, it was centrifuged to clarify it, concentrated via tangential flow filtration, and then frozen in aliquots for subsequent experiments. On the day of experiments, we would thaw the virus, spike it 1 to 10 in an artificial saliva that followed the ASTM E2721 recipe, and then load into a syringe for the aerosol experiments. This is a schematic of the aerosol sampler test system that was developed for these particular studies. This is something very similar, was previously utilized for the Ebola study that I mentioned earlier. But essentially, we utilized a 2-fluid single pass nozzle called the Lee nozzle, used the syringe material to feed at about 300 microliters per minute into the nozzle, and supplied air to the nozzle about 45 psi, which resulted in about 13.6 liters per minute, and provided dilution air to the entire test system at about 34 liters per minute. So the aerosol was able to mix with the dilution air and then basically pass through a flow straightener into a sampling region. So this is a side view of the test system. This is a top view of what the sampling region looked like. Within that region, we had essentially 6 different ports where we located samplers across each of the individual ports. On one of them, we had an aerodynamic particle sizer spectrometer, which was used to measure the particle size for all experiments in real time. And then we located each of the samplers across the 6 ports, as I mentioned, with 2 of the ports having 2 of the samplers located. On the back end of this system is a standard HEPA filter and vacuum pump that is utilized to purge the system or maintain flow during experiments. I should point out that all of these experiments were conducted within a Class 3 biosafety cabinet in a biosafety level facility. After each experiment, each sample was recovered and assayed using a TCID50 assay as well as RT-qPCR in order to determine the infectious concentrations of virus in our recovered samples, as well as the amount of RNA from SARS-CoV-2 in all of our samples. Each of the midget impingers prior to experiments was loaded with the viral culture media without 10% FBS. And after each experiment, 10% FBS was spiked back into it. That was to avoid any bubbling or foaming due to the FBS during sampling in the impingers, which would cause us to lose sample through the outlets. And then each of the dry samplers, after experiments were completed, were recovered into the appropriate volumes per stage per the manufacturer guidelines with viral media plus 10% PBS. And those were then sent over to perform the assays in the laboratory. We also did a subset of experiments in order to characterize the specific test system itself. In the first set of experiments, we utilized a fluorescent tracer, ammonium fluorescein, spiked into simulated saliva in order to generate aerosol particles that were similar in the particle size that we would achieve with SARS-CoV-2 in the simulated saliva. The first set of experiments, we put a gelatin filter located at each of the sampling ports and use those filters to flow at the same flow rate for the sampler that would be located there. These experiments were intended to measure the uniformity of the aerosol in the sampling region to ensure that we didn't have any bias due to the experiment itself. In a second set of experiments, we also used the fluorescent tracer, with each of the samplers located at each of the ports, with the intent of being able to determine the physical sampling efficiency of each of the samplers in each of their locations in order to be able to determine the difference between the infectious virus concentrations and the losses of the virus that were simply due to the physical sampling efficiency, since our goal was to identify which particular sampler was best for maintaining the integrity of the virus during sampling. Our experimental design was very simple. Essentially, we provided air and liquid feed to the nozzle for 1 minute into the test system to achieve a steady state. After that minute, all of the vacuums were turned on to the samplers and they were allowed to draw aerosol for 3, 13, or 33 minutes. We looked at 3 different times to see if the integrity of the virus would change in any of the samplers over longer sampling periods, which would be representative of some of the studies that were looking at long-term environmental sampling in some of the clinical settings. After the 3, 13, or 33 minutes, the vacuum to the samplers was stopped and the system was allowed to continue to purge until we reached baseline levels within the system. The samplers were then removed and recovered in culture media and sent off for analysis. Within our system, as I mentioned earlier, we did utilize a TSI APS 3321 with a diluter in order to measure the aerosol size distribution during experiments. The MMAD of SARS-CoV-2 in the artificial saliva was about 1.54 microns, which falls within the range of what has been reported for the aerosol particle sizes that are expected from coughing, speaking, and breathing from previous studies. The GSD in the system was about 1.53 for those particle sizes. On average, our temperatures were 23 degrees C across all our experiments, and the relative humidity in our experiments was about 34% across all the experiments. So this is a summary of the test system performance. Again, we looked at the sampling locations and the efficiencies at each sampling location to ensure that we had uniform mixing in our test system and would not bias our study based on the test system experiments themselves. What we basically saw was that all locations were statistically the same except for location 7, which was slightly lower, about 71% versus all of the other locations. For the physical sampling efficiency, where we had each sampler at each location and sampled with the ammonium fluorescein, we actually saw statistically different physical sampling efficiencies for the glass midget impinger compared with all the other samplers, and the PFA midget impinger, which was significantly lower than the biosampler. All of the other samplers were pretty similar in terms of their physical efficiency. Now, these 2 values, the sampling system efficiency for the location and the system efficiency for the specific samplers, were then utilized to adjust the concentrations of SARS-CoV-2, which I'll show you on the next slide, in order to separate out those physical efficiencies from the performance of the actual samplers for maintaining the infectivity of the virus. Oops, there we go. So on the top graph here, you're seeing the concentration of SARS-CoV-2 in log 10 TCID 50 per liter of air across each of the samplers. The impingers are located, the first 4 samplers are the impingers, all glass impinger, biosampler, glass midget, and the PFA midget impinger. And then the last 4 are dry samplers, the Ciotis impactor, gelatin filter, Teflon filter, and the BC251. These are the raw concentrations of SARS-CoV-2 measured before adjusting for the location and sampler efficiencies. This dotted line at the top is about 3.5 log 10 TCID 50 per liter of air. And this is the theoretical maximum concentration that could have been measured in the system based on what we loaded into the syringes and generated into the system and the airflow rate of the system. And as you can see, the glass midget impinger is significantly lower than all of the samplers that were evaluated. And the PFA midget impinger was significantly lower than the biosampler. When we adjusted for the physical losses and the system location efficiencies in the system, we see that the glass midget impinger continues to still be significantly lower than all of the other samplers. And the PFA midget impinger was still statistically lower than the biosampler as well as the Teflon filters. The other interesting thing about these data are that the biosampler and the PTFE filter, once adjusted for physical losses within the system, were not statistically lower than the theoretical maximum, indicating that they recovered nearly all of the virus that was generated into the test system. So as I mentioned earlier, we also performed a series of experiments where we allowed the system to generate particle and the samplers to collect particles for an additional 10 and an additional 30 minutes. So what you're seeing here are the concentrations of SARS-CoV-2 in log 10 TCID50 per liter of air. Again, these 3-minute data are the ones that you saw previously, and then for the additional 13 minutes and 33 minutes. Now, the all glass impinger lost significant concentrations of SARS-CoV-2 across 3 and 33 minutes. The biosampler was able to maintain the integrity or infectivity of the virus across the entire time that it was sampling. The glass midget impinger also lost significant virus concentrations between the 13 and the 33-minute sampling period, or the 3 and the 33. The Teflon filter actually lost significant concentrations between the 3 and the 13-minute period, as well as the 13 and the 33. And interestingly, all of the dry samplers in this particular study did not lose any infectious virus titer over the course of 33 minutes of sampling. So it's not, we did not go out past 33 minutes, so it's not entirely necessarily informs longer sampling durations, but at least within the time periods that we evaluated, the impingers, generally speaking, did lose significant material over the course of time, with the exception of the biosampler, which, as I mentioned earlier, is intended to be a softer impingement and swirling motion within the impinger itself. We also recovered the samples from our 3-minute and 33-minute experiments and evaluated the concentration of RNA in those samplers versus time. And so what you see here again is the log 10 RNA copies per liter of air for SARS-CoV-2 in each of the samplers for 3 and 33 minutes. In none of the samplers do any of the concentrations of RNA significantly decrease over time. Which is an interesting result, because we know that we saw losses of concentrations of infectious virus material across those time periods from our previous plot. So what this indicates to us is that the virus itself was not physically being lost, for example, from re-aerosolization or bubbling in the impingers, but was rather being inactivated in some way in the all glass impinger, the glass midget impinger, and the PFA midget impinger, due to some mechanism inside the impingers over the course of time. It also means that, based on a lot of the studies where RNA has been sort of utilized as an indication of the presence of SARS-CoV-2, it very simply means that they don't necessarily correlate in either direction, positively or negatively, and that one should not be used necessarily to inform the other, and that they do need to be somewhat assayed when possible separately. And the last piece I want to talk about is the size-selective sampler. So as I mentioned earlier, the SIOTUS sampler was utilized for some preliminary studies that were done early on to look at concentrations and size distributions of SARS-CoV-2 RNA in different clinical settings, as well as the NIOSH BC251. In our studies, the different stages of the SIOTUS are shown here, along with the recovered concentrations of SARS-CoV-2 on each of the stages. So the SIOTUS measures particles greater than 2.5 on that first stage. I believe the upper limit of that particular inlet is somewhere around 10 microns, and then it has a filter at the end that's supposed to measure particles, basically capturing everything that's greater than 0.25. And you can see here, as you recall from our APS measurements, that the distribution of our particles was about 1.53 microns, and the majority of the aerosol or infectious SARS-CoV-2 virus is measured in the size range in the SIOTUS that we measured with our APS, or characterized with our APS. In the BC251 NIOSH sampler, it has 3 particular size bins. The first stage collects particles greater than 4.5 microns. I believe the upper limit of that is somewhere around 10 as well, with the lower stage being a filter collecting particles basically that don't land on that last stage, which is 1.5 microns, and anything that will be sampled by that particular filter. Similarly, again, we see that the majority of the particles for SARS-CoV-2, or the virus for SARS-CoV-2, is also measured on that middle bin where the particles should lie, based on the MMAD, or aerosol distribution, measured from our APS. So I wanted to just talk a little bit about why these types of data are important and sort of kind of a quick and dirty calculation of how these could influence the risk estimations. So this is sort of my cartoon of how this all comes together, but let's say we have an infected population of individuals and we are characterizing the concentration of SARS-CoV-2 around these individuals to try to determine the amount of material that's in the air. If, for example, our researcher had utilized a midget impinger, as we've shown, which had a significantly reduced performance for measuring infectious SARS-CoV-2 aerosols, and measured a concentration of about 1.8 log T-STAT-50 per liter of air, utilizing that sample in this particular field study, assuming that your susceptible host is over here breathing at 6 liters of air per minute, and knowing that the infectious dose for SARS-CoV-2 is somewhere around 1,000 or 3 logs. And I will not debate that with anybody here today because there is a wide range of numbers that are being reported for SARS-CoV-2. But assuming that this is a reasonable estimation of the ID50, this particular individual would receive an infectious dose in about 2.6 minutes. These individuals would receive an infectious dose in about 2.6 minutes. When in reality, if the concentration had been measured with a bioaerosol sampler and actually been reported for what it really was, in this case, remembering that the biosampler measured nearly 100% of the aerosolized SARS-CoV-2 in our studies, you would start to see a realistic concentration of these aerosols. And now you would see that this particular individual would in fact receive an infectious dose in 5 seconds. So this speaks a lot to the accuracy of the data that then we provide into our models in order to predict risk and to also determine what level of mitigation would be needed in order to reduce the risk for this individual because of the infectious dose that they would receive, and a miscalculation based on the way that that particular source or concentration in that environment was measured. This is just a very simple sort of way to highlight why it's important to understand the limitation of the bioaerosol sampler that you are utilizing in your studies, and to be able to compare that in order to try and make correlations between things like infectious dose and source able to tick and tie as we develop these models and we develop countermeasures in order to mitigate the influence of respiratory or other aerosolized infectious diseases. So I'd like to summarize by pointing out some generalizations on which particular samplers performed the best in our study. So in general, the biosampler, the SIOTUS impactor, the BC251 gelatin filter, and Teflon filter did not see any losses in concentration of SARS-CoV-2 as a function of time, as I showed, but they also were not statistically different from one another. Albeit the biosampler and the PTFE filter actually were able to recover nearly 100% of the virus that was generated. So generally speaking, these would be recommended for studies where a low flow laboratory scale aerosol sampler is required, with the caveat that we only performed our studies at 1 particle size, approximately 1.5 microns. And for example, you may see some additional benefit for samplers like the glass midget and PFA, where physical sampling efficiency is low for that particle size, but you may see an increase of the physical sampling efficiency. But we did also see, conversely, the loss in infectious material of SARS-CoV-2 in those 2 samplers as well. So generally speaking, probably want to avoid the general impingers, but the biosampler itself was a very good performer in terms of sampling for SARS-CoV-2. I'd also like to point out again that RNA did not necessarily correlate with infectious virus concentrations in our particular study. Unfortunately, as I mentioned, we needed to perform our studies with the samplers that we had available to us at the time. There are so many other samplers that have been utilized out there, especially large scale samplers that are more intended to be able to have a higher concentration factor. It would be great if we could actually study those as well to be able to inform comparisons for those studies that have been looking at high volume sampling and larger spaces. And again, we only utilized 1 particular particle size in our study. So additional studies should be performed. I should also note that there may be some influence of the particular media that was utilized in our studies that may speak to the survivability of the virus, but that's sort of a tangent I don't really want to go into today. And with that, I will conclude presentation on this particular study. If you wanted additional details, please feel free to go to the ASNT website. This particular study is posted on there. This manuscript was published, I believe, sometime this last summer. I'd like to thank all of the brilliant scientists that are at the NBAC, the contributing authors that helped with this study. This particular study was performed under the guidance of the DHS Panther program. There's a link down here below if you want to learn more about what the DHS Panther program is doing with respect to research in SARS-CoV-2, as well as any other future studies. I'd like to thank Dr. Bill Lindsley again for loaning the NBAC our BC251 samplers that we were able to utilize, and also the leadership at the NBAC as well. And before I jump to any questions, I do want to give a plug to two things that I can't see here at the top. But first, this particular paper was also included in a curated collection in ASNT on COVID-19 and aerosols. So I would encourage everyone who is performing research out there related to COVID-19 and SARS-CoV-2 to check out the curated collection. There's some really great studies in there that are very informative, and also encourage researchers out there to submit to the journal to be included in the curated collection. And the upcoming AAAR conference in Raleigh, North Carolina, I did want to give a plug to our special symposia for aerosol science and infectious diseases. It's been 2 years. We've had 2 conferences, I believe now, with symposia related to SARS-CoV-2. We've learned a lot as a community, and it will be exciting to see sort of what we have learned and what we still need to learn and communicate across the various researchers in our community at this next conference. So I highly encourage you to please submit abstracts on any new research that's being conducted on SARS-CoV-2, and to attend. There'll be some panel sessions as well where we can talk a lot about the science. And it's one of the few opportunities where we get to get very technical when it relates to aerosol science and public health. So I look forward to seeing all of you in Raleigh this fall. And with that, I see a lot in the chat. So
Thank you, Professor Shana. That was an enlightening talk. We can move into questions from the audience, or if you have questions, I see them in the chat. I can read them out if you want, or if people have questions, speak up.
Okay, I see Lindsay's. She asked, what was the RH in the system? It was 34% on average across all the experiments. And so, as I know many of you are aware of, we were hoping to keep that below what we consider the efflorescence point for sodium chloride, so that we could assume that the particles were fully dry in our experiments. And we were able to achieve that with the syringe feed rate that we were utilizing and the dilution airflow rate. Ooh, what was the SARS-CoV-2 concentration, TCID50 and RNA while injecting into the main sampling tube? I don't remember what the RNA concentrations were. I apologize off the top of my head, but I do believe that the concentration of virus that we generated in terms of the TCID50 may have been 5 log 10 TCID50. Trying to remember that off the top of my head. It was 5.7 actually, once it was spiked into the simulated saliva. And I don't know the RNA concentration, but I do think we have that information somewhere. There's a question from Dewanash, and he asks, or was wondering, since the samplers have different flow rates, was the inlet of the sampler isokinetic? No, we did not design the system to be isokinetic. That is why we did the location system efficiencies and the sampler system efficiencies, physical efficiencies, and then we're able to adjust the SARS-CoV-2 concentrations based on those, because they were not designed to be isokinetic. what was the collection media used in the SKC biosampler? The collection media was the viral culture media. So it was the minimum essential media or complete growth minimum essential media that we utilized. And it did not have the 10% FBS because we were trying to avoid foaming. I see the second part of the question was, did you add any anti-foam? We did not add any anti-foam. So it was basically the minimum essential media. And then after we recovered the virus, we would add FBS to it to get that 10% FBS and then basically culture it, assay it for the TCID50 and RNA. Addition of a chemical earlier in your presentation, but missed it. I think you're talking about the ammonium fluorescein that was utilized in a separate set of experiments as a physical tracer, but those studies were performed unpaired. So the physical efficiency studies had ammonium fluorescein spiked into the culture media, and we actually added 7.5% FBS, I believe. And that was just so that we could achieve that same particle size that we intended, or that we knew that we would get with SARS-CoV-2 spiked into the artificial saliva, actually. But we did not add any chemicals to the material that we aerosolized during the SARS-CoV-2 experiments. Performance of size-selective. Okay, so there's a question about performance of size-selective selectors. To what extent will the size distribution itself influence these results? That's a great question. We obviously, SARS-CoV-2 aerosols span a very wide size range around infected individuals. Yes, we only measured 1.5 microns. So I would say that that is one of the reasons why we focus primarily on the infectivity of the virus during collection and try to eliminate the physical sampling efficiency that is very much a function of the particle size distribution of the aerosol. So we were really just focusing on the SARS-CoV-2 particle sizes that were 1.5 microns and looking at the infectivity there. So I can't really say how we would see differences in the larger particles in terms of its infectivity, except to say that I think that generally speaking, I think impingement would hold as not necessarily the best way to sample SARS-CoV-2, both in short-term and long-term sampling, just based on the losses that we saw. There's some mechanism once it's sampled that's causing a loss of the infectious virus. But obviously the physical sampling efficiencies are going to vary. So larger particles are not going to be as efficiently sampled for some of these, and conversely, smaller particles. I think that most of these samplers' physical efficiencies are pretty well characterized, but definitely would encourage any researchers out there to preliminarily characterize the physical efficiencies of their samplers before they utilize them in their specific scenarios for their studies. Let's see. Great question. Why do you think wet samplers were losing sampling efficiency with increase in sampling time, but the sampling efficiency with the filter system were not decreasing with increasing sampling time? So I don't know for sure, but my theory, which is open to debate, is that some process of the impingement and agitation of the fluid during sampling in the AGI midget and the two midgets is likely the cause of some sort of stress on the virus that led to losses in infectivity. I do think that while we didn't see losses in the filters or the dry samplers over time, that maybe had we allowed the samplers to go out for longer periods, potentially if it was at a different relative humidity, you may see an influence there, but at least within the conditions and the way we performed our study, we did not see that for the dry samplers. I know that in the past, some studies have reported, especially for gram-negative bacteria, losses due to desiccation, or at least that the theory is that it's due to desiccation with some of the drier samplers. But in this particular study, we did not see that, at least within the conditions that we tested. It may be that the way we aerosolized the virus in the MEM with the saliva, that there was some amount of protection once it had dried initially that allowed for it. I actually don't know, but there is something there that is going on that's allowing the virus to stay at least infectious for 33 minutes in the dry samplers. And in the biosampler, because we don't see a lot of losses in there, it leads me to think it has to do with the impingement process and the agitation of the fluid. Someone asked a question on viability as a function of size. So that's a big question and a whole nother can of worms. I think that there are some studies that indicate that particle size can influence the survivability of the organism entrained within the particle. That may be due to shielding. It depends on the condition, like if we're talking about outdoors in sunlight versus indoors, partitioning of the virus or movement of the virus throughout the particle, whether it goes to the surface or stays entrenched. There's a lot of work being done, I believe, by the University of Bristol on that, and they're probably better equipped to answer that. But I do think that there is going to be an influence on the infectivity of the virus as a function of particle size, but not a whole lot is currently done specifically for SARS-CoV-2 in that arena. Did you make any changes to the RNA extraction protocols to account for the various types of samplers? No, we did not. They were all recovered in either the MEM plus the FBS or sampled into the MEM with the FBS added, and then they were all processed in the same way. Okay, there's just a comment about bubble bursting in impingers. So that speaks to why the particular impingers may have been causing loss in infectivity of the virus. And I believe that is the last comment question in the queue. Wait, oh. How much time do you take to process a sample after sampling? Okay. So first question, how much time does it take to process the sample after sampling? After the system was purged, which usually took about, I would say maybe 2 to 3 minutes, the samplers were taken off the rig. The liquid samplers were immediately poured into a conical tube, and the dry samplers were all recovered in the culture media, and those were sent to be assayed within an hour. Those assays were started. I do not know if those were done so rapidly. I'm not sure that we ever turned around and looked at if we had allowed them to sit. Would that have caused a loss in the infectivity, to be honest with you? Although I would say there's, yeah, we never looked at whether there was a loss because we usually recovered our samples and basically performed our assays almost immediately. And have you considered repeating the study with influenza virus? So there are a number of studies that have been done with influenza virus, not necessarily with these specific samplers. I know that Dr. Bill Lindsley has done a number of studies on influenza. So I haven't personally considered doing it with influenza, but I think these types of studies should be done almost before anyone does any studies with any particular infectious material or bioaerosol to understand for their particular study, which is going to give them the highest concentration, which is the closest to reality, since you can't make up fake numbers when it comes to these assays. So I do encourage everyone to do these studies specific to their bugs, to their particular particle size distribution, and their particular experimental setup. And Dave says, if anyone wants to borrow an AirPret, please contact him.
Yeah, we'll pass the message. Okay, is there any more questions? If you want to speak up or type in the message, the text chat, we'll have some more time. Okay, maybe that's all. I believe that was an interesting discussion at this time, and I would like to thank everybody for being here, and hopefully we'll meet you in next ASNT lecture in May, and this recorded lecture will be available to everyone in the future. We can pass them out. And Professor Shanna, thank you for your time and sharing your knowledge and experience with us. I know we'll be seeing you in this year's AAR conference. She serves as the chair for AAR Education Committee and the co-chair for Aerosol Science of Infectious Disease Special Symposia. Thank you.
Thank you, everyone.
Well, thank you. It was a really great, wonderful talk, Shauna, and great job with the questions. That was a really wonderful discussion and very informative. So thank you both.
All right. Thank you, Amy. It's nice to see everyone. Bye.
We had a big audience. That was very good.
Yeah, there were over 80. There were over 80 people.
Yes.
Good. I was trying to see, but I couldn't. It's hard when you're in presenter view to really try to count
It's hard to see the
people.
messages at them. Exactly.
Yeah.
But yeah, no, it was wonderful.
Good. Great. Thank you. Thanks for the opportunity. I probably won't watch the video because I hate hearing my voice. So.
No, you were great.
So, all right. Well, I'm sure, Amy, I'll be talking to you a lot in the next few weeks. Good luck with everything. I know you must be very busy, and it was nice to meet you, Chaitani. I think I got it. Did I get it? Close? Okay.
No problem.
Yeah, take care, everyone. Thank you. Bye-bye.
Should we end the meeting from our end?
Oh yeah, you can go ahead and end it. Yep. Thanks for the great job.
Thank you, Amy. We'll see you.
Bye.